one of the two is a smoker and the other one is not, and hence they are incompatible. Smokers don't like non-smokers, and non-smokers detest smokers. They just don't mix. They're incompatible. Well, it's just by analogy. Now, in the context of quantum mechanics, two observables, let's say A and B, generalizing, they are compatible if they can both be measured to infinite accuracy simultaneously. Okay, that's the definition of compatibility. And by implication, the opposite of that is when you cannot measure both observables A and B with infinite accuracy simultaneously. So the Heisenberg uncertainty principle is a principle about incompatible observables. Right? In the concrete case of where A and B are the position and the momentum, right? The x and your p, if you like. Okay? So the x component of the momentum, p of x and x, that's a pair of observables that are incompatible. And we didn't talk too much about it, but there's another Heisenberg uncertainty principle relating measurement of the energy and the time at which you measure that energy. Those two also are incompatible. All right? Now, I'll give you some examples of pairs, because it's interesting talking about pairs. You know, the very notion of compatibility implies it's within the context of at least two things, right? You can't have one thing being compatible with nothing else. It doesn't make any sense. You have to have at least, you're talking about two things, okay? So I'll give you some examples of pairs of observables, measurable physical quantities that are compatible, that you can measure them both simultaneously with with as much precision as you want, to infinite accuracy. Okay. Well, the different components of momentum, those two, that might surprise you a little bit, but those two are compatible. And here you've got position momentum, but it's not the x component of the momentum, it's the y component. So the position along the x-axis and the y component of the momentum, they are actually compatible. You can measure them both simultaneously with as much accuracy as you want. Okay. The energy and the momentum also you can measure compatibly. What's the adjective? All right. Okay, so that gives you the notion of compatible and incompatible. Now, that's sort of a hand-wavy, verbal type way of thinking. How about, question, is it possible to find a mathematical, expressed mathematically, a mathematical criterion for compatibility or incompatibility between two observables? Now, since we're looking for a mathematical criterion, let's translate the observables, say A and B, into their corresponding operators, so A hat and B hat, because remember one of our really core ideas in quantum mechanics has been the importance of the Eigen Equation. So for each observable there's a corresponding operator. So for observable A there's a corresponding operator A hat that you plug into an Eigen Equation that gives you, and you solve it for its eigenfunctions, which give you the allowed wave functions of that quantum system. and the eigenvalues, which give you the allowed quantized measurement values. Right? So a really core idea. I repeat deliberately for reinforcement. These ideas are really important. All right. So suggestion. Let's try to find some mathematical criterion that can tell you yes or no whether two observables A and B are compatible or not. And we will use their operators, A hat and B hat, in this mathematical criterion, whatever it is. You know, we haven't found it yet, we're just starting, and it'll go on for sessions, believe me, it's very important and quite a lengthy process. But I'm giving you the beginnings, you know, the initial stepping stones towards that. All right. So we want this mathematical criterion, and how to find this criterion. Some mathematical device that we can use, and we plug in the two operators for A and B, these two observables A and B, and then we crank the handle. You know, we use this formula, this criterion, whatever it is, and out comes the answer: compatible or incompatible. But how to do that, right? Well, a bit of revision, because we're going to need it next couple of sessions. You may remember that if you're trying to measure the allowed values, the eigenvalues of observable A, right? When the wave function that you're talking about is a general, and that just usually means superposed, right? So here's your superpose of general wave function or state, okay, psi, and you write that as a weighted sum of orthonormal eigenfunctions of the observable operator, in fact A hat. So the observable is A, like momentum, position, charge, energy, spin, whatever, you know, whatever the observable is. Okay, observable A, its corresponding operator A hat. So here's your Eigen Equation. Okay, here are the allowed measurable values of the observable A, the eigenvalues. Okay, so when you take the measurement, now you'll get one of these results, lambda. You'll get the result. The measurement result will give you one of these, and the probability that the result, the measured result, is lambda I, is this coefficient here squared. Right? Basic idea of quantum mechanics. Okay, so and then I think it was von Neumann actually pushed this idea, the idea of the collapse of the wave function. So after the measurement, the wave function, state, is no longer this general form psi. It's one of these eigenstates. So psi collapses, it changes rapidly from this to one of these. Okay? So psi collapses to one of these eigenstates. This psi I, which is the eigenstate corresponding to the eigenvalue lambda I, and that's the measurement result. Okay. Now that's just revision, but we're going to need it again pretty soon in trying to find a mathematical criterion, a test if you like, mathematical test, whether two observables A and B, or their corresponding operators, A hat and B hat, are compatible or not. Okay. All right. Well, now we're talking about compatibility and incompatibility. So we need to talk about two observables, so A and B, right? And with their corresponding operators that you use in the Eigen Equation for each, A hat and B hat. With their Eigen Equations. Now I'm looking up. You can't see it, but the next session, just to give you a lead-in for what's coming. We'll use this idea of collapse of the wave function for two successive, one after the other, measurements. Right? We'll perform a measurement on observable A, followed immediately by a measurement on observable B. And then we'll do the reverse. We will perform first a measurement B, and then immediately after perform a measurement A. And why am I saying this? Well, it's a clue to this mathematical criterion. Well, I'll throw it at you. When A and B, these two observables, are compatible, measuring A then B gives you the same outcome as when you measure B then A. Okay? But when you have two observables that are incompatible, then measuring A then B gives you something different from measuring first B then A. Right? So that's a pretty strong hint towards creating a criterion, a mathematical test, whether two observables A and B, or actually their corresponding operators, A hat and B hat, are compatible or not. Right? So we need to go to the next session to just follow on from here.